Hi, Assalamualaikum. Good morning. I'm going to continue my lecture on CHM676, which is organometallic compounds. I'm going to talk about binary carbonyl compounds or binary carbonyl complexes. And when we talk about binary, usually what comes to mind is the number two. Binary carbonyl complexes are classified as homoleptic complexes. Now, there are two terms here that I would like you to become familiar with. The first term is binary complexes, and the second term is homoleptic complexes. Now, binary complexes are any complexes that are made up of two different types of fragments. Whereas homoleptic complexes are complexes that have the same type of ligand, only one type of ligand, and they're the same. So usually a binary carbonyl complexes a binary carbonyl complex is a homoleptic complex, because a binary complex, for example, nickel tetra tetracarbonyl nickel, has only two fragments, which is the nickel fragment and the carbon monoxide ligand fragments. And because there are no other ligands there, it can be classified as homoleptic, because homoleptic is having the same kind of ligands. So if, for example, your nickel CO4 becomes nickel CO2 Cl2, for example, then that's no longer binary, because you have three components or three components there. You have the nickel component, carbon monoxide component, as well as chloride component. And it is also no longer homoleptic, because there are two types of ligands in there, which is the type of carbon monoxide, and the second type is chloride. Yep. So I hope those two terms are clear to students now. In these notes, it is said that the binary carbonyl complexes are mostly available commercially. You can buy them, and they are very useful starting materials for preparation of other organometallic complexes. And there are many ways to synthesize metal carbonyls. The first is by direct reaction of metal to carbon monoxide, in this situation, for metals or transition metals, only iron and nickel are capable of reacting directly with carbon monoxide under mild condition to give FeCO5 and NiCO4. There you are, you have iron with 5 carbon monoxide, nickel with 4 carbon monoxide. Why are those numbers? Why 5 and why 4? We're going to talk about it soon. Yeah. Both complexes are very toxic because they easily undergo thermal decomposition to release carbon monoxide, a very lethal gas. And in the previous lecture, I have mentioned to you, or I have explained to you, why carbon monoxide gas is lethal to human. I hope you can recall why that is so. That is the first way to synthesize metal carbonyls, by direct reaction of metal with carbon monoxide. The second type would be that well documented is the reductive carbonylation, where the formation of this chromium carbonyl is through reduction of this chromium. So this chromium is a chromium 3, whereas that chromium in the product is a chromium 0. So from 3 to 0 is a reduction. So it is a reductive carbonylation. And also it can be from from metal halide. It can be also reductive carbonylation from metal halides, like the second one. And high nuclearity carbonyls. What do I mean by high nuclearity? High nuclearity means that there are many metal centers in the same carbonyl compound. Yeah, many metal centers. For example, here you have a mononuclear osmium CO5 heated uh, um, uh, under high temperature, you get a trinuclear. So you have osmium. There are 3 osmiums in this product. So you are increasing the nuclearity of this osmium from 1 osmium per molecule into 3 osmiums per molecule. And the same can be induced to happen not only through heat, but also through light energy. So those are the ways in which binary carbonyl complexes are formed. And there are many more. These are just examples. Now, I hope that is clear to you. I would really next like to go into quite an important part of this course, which is the 18 electron rule. The 18 electron rule, or sometimes called the EAN rule, effective atomic number rule. EAN is effective atomic number rule. This is actually the transition metals answer to octet rule. So any student studying chemistry must have heard of octet rule. Yes, the octet rule is the rule that says that all elements will react to one another until they reach octet, or until they reach 8 electrons on the outer shells, just like the noble gases. But 8 electrons are not going to be enough for transition metals, because for transition metals they have d orbitals. The 8 electrons, the octet, are actually designed for representative elements where you have s and p orbitals. 1s and 3p orbitals make make 4 orbitals, and 4 orbitals can be occupied by 8. Um, maximum number of 8 electrons. That is why it is called the octet rule. But when you add d orbitals into the picture, there are 5d orbitals, an addition of 10 more. So that is why for transition metals, to achieve stability, they need to have 18 electrons on their outer shells. Yeah. So to achieve stability, most transition metal carbonyls have to obey 18 electron rule. Not only carbonyls, but other as well, other transition metal complexes. 18 electron rule. This is because there are 9 valence orbitals to be filled for the transition metals. In the case of the first transition series, these are the 3D, the 4s, and the 4p, the 4s and the 4p plus the 3D. So there are 9 orbitals. Multiply that by 2, because each orbital can be occupied by a maximum number of 2 electrons, making it 18. So this rule can be formulated in terms of total number of electrons around the metal, in which case this number is usually found to be 36, 54, or 86, corresponding to the atomic number of the noble gas. Now we go back to noble gases. We go back to the supermodels of elements that live on the 8th group. Yeah, the last column in the periodic table. 36 is the atomic number for krypton, 56 is xenon, and 86 is radon. The metals are then said to have the effective atomic number, or EAN, of the noble gases, or they are said to obey the EAN rule. because the pseudo-noble gas valence shell for krypton, xenon, and radon contain 18 electrons. What do I mean by pseudo-noble gas? That means the valence electrons, yeah, the valence electrons. It is just simpler to count the valence shell electrons as 18, yeah. So for transition metals, for them to achieve stability, they must have not 8 electrons on the valence shell, but 18 electrons. That is why we have the 18 electron rule for the transition metals. Now, before we go far to count electrons, we must first understand what are the d electrons. Yeah. Previously, when we are learning about counting electrons for transition metal, we understand that the periodic table is filled in the order of 4s to 3d10 or 3d1, 3d2 until all the way to 3d10. This turns out to be true only for isolated metal atoms. So when metal atoms exist just by themselves, not surrounded by any other ligands or uh, um, ions, uh, this is true. That means the 4s is filled up before the 3d. Yes? But when we put a metal ion into an electronic field, that means we surround it with ligands, the d orbitals drop in energy and they get to be filled first. So the d orbitals will have a lower energy than the 4s when the metal has ligands surrounding it. Therefore, the organometallic chemist considers transition metal valence shell to all be d electrons first. Lastly, then the 4s is filled. Yeah. There are certain cases where the 4s to 3dx order does count, but we can neglect this in our first approximation. Therefore, when we ask for the d electron count of the transition metals, such as titanium, in the zero oxidation state, we call it d4 and not d2. If you refer to periodic table, so periodic table is way down at the bottom of our notes. Yep. Oops, sorry. Down here. So titanium, traditionally we understood that it is 4s2 3d2, but since organometallic compounds are surrounded by ligands, so the 4s becomes higher in energy than the 3d, so the 3d becomes filled in first. So titanium 0 in that case will have 4d orbitals, and the number of d orbitals can be happily coincided with where the metal is located in the periodic table according to these columns. So if it is on the fourth column, that there are 4d orbitals for the element, but when you have the oxidation happening, then as per usual, you will lose electrons for metals. So titanium 0 is 3d4. Titanium 2 would be 3d2 because 2 of the electrons will be lost. For example, vanadium 0 will have 5d orbital electrons, whereas vanadium 2 will have 3d electrons. I hope that is clear to you. So I'm going back to all the way up to the top for the counting of, excuse me, I'm making you dizzy, counting of the d electrons. So for zero valent metals, we see that the electron count simply corresponds to the column it occupies in the periodic table. Hence, iron is in the 8th column and it is D8, not D6. Rhenium 3 plus is D4 because it has lost 3 electrons. Otherwise, rhenium 0 would be D7, 7th column for rhenium, and then add 3 positive charges or subtract 3 negative ones. Now that we can assign a d electron count to the metal center, we are ready to determine the electronic contribution of the surrounding ligands and come up with our overall electron count. So to count electrons, there are very, very simple steps. The first one, there are 4 steps that you have to look at. The first is to count 2 electrons and 0 charge. We are starting with carbonyl. So carbon monoxide is the simplest ligand for carbonyl. So carbon monoxide is a 0 charge. Obviously, carbon monoxide is a neutral molecule. It doesn't have any charge, and it donates 2 electrons to the metal. If you still remember the mechanism of bonding in the sigma bond formation, the carbon monoxide donates 2 electrons to the metal. So carbon monoxide is a 2 electron donor with a 0 charge because it is a neutral molecule. For charge and number of electrons donated by other ligands, see table 1 on page 11. I'm not sure whether this is still page 11. Let's have a look. Is it still on page 11? No, it's no longer on page 11. It is now on page 12. There you go. This is the table that you should refer to when you want to know each ligand, how many valence electron is contributed by that particular ligand and what are the charges. For example, your hydride here. Hydride is 1 negative charge and it donates 2 electrons. Similarly with fluoride, chloride, bromide, iodide, these are all carry with them 1 negative charge and they donate 2 electrons. Cyanide, thiocyanide. These are similarly like the previous ones that I talked a minute ago. Carbon monoxide is a neutral molecule, so that's 0 charge. Cyanide, also 0 charge. Nitrosyl, also 0 charge, and so on. If you don't see any charge, then it is a neutral molecule. But alkyl, R minus is an alkyl, for example, methyl or ethyl, they are carrying with them 1 negative charge and they donate 2 electrons each. Yeah, aromatic ring is also the same when they act as aryl. Yeah, a phenyl, for example, it is a 2 electron donor and it carries with it a negative charge. For a 4 electron donor, this is a typical ligand that has 4 electron donor, and 6 electron donor this is another typical ligand. So that is on page 12. Let me change that in the notes so you don't get confused. Second. Excuse me. More dizzy people. On page 12 in this case. Yep. Now, step number 2, for a compound with more than one metal center, if we are counting electrons for the compound as a whole, each metal-to-metal bond counts as 2 electrons. But if we consider each metal individually, we count 1 electron for each metal-to-metal bond. This will become much more clearer when we discuss examples later. Rule number 3, find the number of d electrons that formally belongs to the metal atom alone, the one that we discussed up here. How do we count the d electrons? If the metal is neutral, i.e. it is not charged, the number of d electrons is the same as its location in the periodic table. If it is a positively charged metal center, then you subtract 1 electron, you minus 1 electron. But if it is a negatively charged metal, you add 1 electron. So last You add together all the electron counts you get from step 1, step 2, and step 3. If the total number of electrons is 18 per metal, then the compound can be considered stable. Yep. So 18 is the magic number for stability. If it is less than 18, it is unstable. If it is more than 18, it is also, that compound is also unstable. So I'll give you a very simple example. For example, molybdenum CO6, see figure 1 on page, I would say this would be page 9. See figure 1 on page 9. Here you are, we have figure 1 on page 9. The molybdenum in here with 6 carbon monoxide. So when you are drawing 6 carbon monoxide around a metal center, remember you must draw the bond from metal to carbon. You cannot draw the bond from metal to oxygen. So you would be tempted to draw this part as CO, but be very diligent to draw C bonded directly to metal and oxygen away from the metal. And if you have 6 bonded pair around a metal center, obviously the drawing would be, the geometry of the molecule or the complex would be octahedral. So in cases like this, remember this is what is the drawing look, what it looks like. I'm going to introduce to you how to count the electrons. Now, to count electrons, I always recommend that you come up with a little table with 3 columns. The first column is for fragment, the second column is for charge, and the third column is for number of electrons. So if you can still recall the MOCO6, this one, I'll just take this into the picture so that you are okay with it. My face a bit like that. And go back there. And just put the picture that's next to this counting so I can explain to you clearly. Insert a box here and stick it there. I'll make it small. Yeah, that's it. It's a little bit better. You can see it now. You can see it now. So, what are the fragments that you can see in this MOCO6? Obviously, you can see a metal molybdenum. I put it 0 here, but we have to we cannot determine it to be 0 right now. But because this is such a simple case, we can immediately see that it is a molybdenum 0 because the 6 carbon monoxide, which is the second fragment, the 6 carbon monoxide are neutral molecules. The charge for the carbon monoxide is 0, so obviously because the whole molecule doesn't carry with it any charges, so molybdenum is also 0. So having molybdenum 0, if you look in the periodic table, you will see that molybdenum is on the 6th column in the periodic table, so it has 6 electrons. This is the electron count for your molybdenum 0. 6 carbon monoxide means 6 times 2 because each carbon monoxide is a 2 electron donor, so that is 12. So when you add up 12 and 6, you get 18 electrons. So having 18 electrons tells you that this compound MOCO6 is a stable compound. Yep, that's good. If you go for the second example, which is Re2CO10, Let me do that here. Just 1 second. Excuse me. And we go up, here, change this to, oops, undo. Okay, so it's not going to have it like that. So we do this like that. That's it. So for this metal in here, for this, when you have Re2CO10, that means two metals and 10 carbon monoxide, you can draw the compound like this. Yep, because this is such a simple, it's not as simple as this for some cases, but for this instance, it is really metal to metal. There is a bridging metal to metal, and each of your metal is bonded to 5 carbon monoxide. See, remember that I put carbon bonded to metal, not oxygen. Yeah. So when you look at this picture, and when you are considering each metal separately, that means you split this molecule by 2. Imagine there is a line following my cursor. You are only considering half of the molecule. When you are considering a single Re atom, you have 3 fragments that you must be noticing here, which is one rhenium here. This is your rhenium here. 5 carbon monoxide, 1, 2, 3, 4, 5 carbon monoxide. And the third one, which is sometimes people miss, is this metal to metal bond. Remember the second rule. When a compound containing more than one metal center, if you're counting each metal individually, each one is counted, each one metal to metal bond counts for 1 electron. So actually, between this metal and that metal, there are 2 electrons. But if you break this bond into 2, 1 electron belongs to this metal on the left and another electron belongs to that metal on the right. So it's half. This is not 2, this is half. Yep. Half of rhenium to rhenium, which is 1 electron. The charges are still 0. I have not introduced to you any charged molecules, so the charges are still 0. Rhenium 0 is 7. 5 carbon monoxide is 5 times 2, which is a 10. And a half, remember I just deleted a 2 there, so you in your note you also have to delete a 2. Half of rhenium to rhenium is 1 electron, which is half of 2. Because this is 2 electrons, this whole bond, you are considering only half of it, so you get 1 electron. And adding up all these 3 fragments, you have 7 and 10 and 1, 18 electrons. So that tells you that this molecule or this compound is stable. But if you are counting for the whole compound, you do not split it into half. What you get is 2 metals, 2 rhenium. So 2 metals are 14 electrons, remember 14. And then you have 10 carbon monoxide. So 10 times 2 is 20. 20 plus 14 is 20 plus 14 is 34. And remember this metal to metal count as 2 electrons. So you have 34 plus 2, 36. 36 electrons for 2 metals. So each metal has 36 divided by 2 is 18. So again, you get the same number. Yep. So it's really, really not that difficult. The third case would be counting electrons on a polynuclear molecule, such as the one that you see on figure 3 down here. That's a figure 3. Let me take that. Yep, take that and put it into this box. Oh, big. Delete that and make this one slightly small. Make it smaller, smaller. That's it. I'm taking your time. Okay, that's it. When you have Fe3CO12, this is too small for you to see. I'm going to make it a little bigger. You will see that there are 3 ions here, Fe3CO12. The 3 ions are connected in a trigonal planar, and you will notice that in this picture here, you have 2 bridging carbon monoxide. There is 1 bridging carbon monoxide and there is another second bridging carbon monoxide. So the other carbon monoxides are called terminal carbon monoxide. Let me read this. The molecular structure of Fe3CO12 reveals 10 terminal carbon monoxide. Terminal means it is ending there. It is not bridging anything, yeah? This is a terminal, this is another terminal, terminal, terminal. Only these 2 are bridging. 10 terminal carbon monoxide and 2 bridging carbon monoxide that connects 2 metal. This is 1 bridging carbon monoxide connecting 2 iron. This is the second bridging carbon monoxide that connects the 2 iron metals. The doubly bridging carbonyls are written as μCO or μ2CO. Mu means oxo. Oxo means bridge, to emphasize that 2 metals are bridged. Hence, the more appropriate formula would be Fe3 μ2 bridging 2 metals carbon monoxide, 2 of them, and non-bridging or terminal carbon monoxide, 10 of them. Each bridging carbon monoxide is considered to be sp2 hybridized and contribute 1 hybrid orbital and 1 electron to each metal. So when we are considering to count electrons for this molecule, let me throw that to the side a little bit. Yep. What is this? Okay. There are 2 types of ions in here. There are 3 ion centers, 1, 2, and 3, but 2 types of ion centers. One is an ion that has no bridging with others, whereas these 2 are ions that look very much like another. They are twins. Like this ion here And that ion there, each one of them has 3 terminal carbon monoxide, 1, 2, 3 for the top one, and 1, 2, 3 for the bottom one. And each one of them are connected to 2 bridging CO. So these two are the twin, or the same environment Fe, whereas this one here is the unique ion center. So when we are considering one of the twins, you can take this twin in the front. You can also take the twin at the back, but I'm taking the one at the front. You can see that there are 4 fragments there. You take one by one. You have one fragment is the ion. The second fragment is the terminal carbonyls, 1, 2, and 3. The third fragment is the bridging CO, half of this and half of that. So 2 of half bridging CO, 1 half and 2 half. And then the third one is, the fourth fragment is 2 of half bridging Fe. Yep. This is 1 Fe, half of it. And this is another one, Fe, half of it. So if you put down all the fragments, the charges are still 0. You are going to see that ion 0 is 8 electrons, 3 carbon monoxide is 6 electrons, 2 times half times 2 is 2 electrons, yeah? 2 times half times 2, because each one bridging is 2 electrons. And another one is 2 times half times 2. Fe is also 2 electrons, also 2 electron count. So you have 8, 6, 2, and 2 make 18 electrons. So this ion here has 18 electrons. This ion at the back, being the same as the one at the front, is also 18 electrons. So now let us determine the ion, the electron count for this unique ion. So it's really very simple. I'm not going to go to the next page. It is there, but I'm going to go quickly with you. If you look at this side here, you have the fragment is Fe0, 4 terminal carbon monoxide, and 2 bridging Fe, but half, because you are only taking half of this bond and half of that bond. So you have 8 plus another 8, so that is 16. 1 from here, 1 from there, so 17 and 18. There you go. It's there. So the unique Fe is also 18 electrons. So you can predict that this compound is stable. But if you want to count the electrons for the whole molecule, let me take this to this page. Coming down here. Oops. Yep, take it to the top. Come on. Top. Yep. If you count everything, you have 3 Fe, 1, 2, and 3. You have 10 terminal carbon monoxide, 4 here, 3 here, and 3 there. 1, 2, and 3. So that's 10. 2 bridging CO, 1 and 2, 2 bridging CO, and 3 Fe bond. 1 bond, 2 bond, and 3 bond. So 3 ion to ion bonds. So you count them all. 3 Fe is 3 times 8, so that's 24. 10 CO is 20 electrons. Yep. 2 bridging CO is 4 electrons, 2 times 2. And 3 bridging Fe is 6 electrons, 3 times 2. You add them all up, you get 54, and the 54 must be divided into 3 because they belong to 3Fe. So dividing 54 into 3 make give you 18 electrons per Fe. Yep, so that's good. So count the valence electrons for this. Okay. So I want now to introduce to you the uh, charged or the ionic ligand. If you encountered before MOCO6, yeah? Yes, in a few minutes ago, I was describing to you MOCO6. If we change one of the CO into chloride, chloro ligand, let's try and see and count whether this compound is stable or not. So again, you come up with the little table, fragment, charge, and electron. You have molybdenum fragment, you have chloride fragment, and you have carbon monoxide fragment. But these ones, the one that I make red is you don't know it yet in the first instance. So first you must put molybdenum with don't know what oxidation state for on in the first instance. Chloride, obviously you know already that chloride has a negative charge, and 5CO. Now, the total charge of this compound is 0. There is no charge outside, so the total is 0. If chloride is -1, carbon monoxide is 0, to make a total of 0, your metal must be +1 charge. That is why you can determine that molybdenum is molybdenum 1. And from molybdenum 1, you can then count the electron because molybdenum 0 is 6 electrons, -1 electron gives you 5. Chloride is a 2 electron donor. See table 1 on page 12. So 2 electrons there, and 5CO gives you 10 electrons. When you add them up, 10 and 2 and 5, you get 17 electrons. So the compound MOClCO5 is unstable. Unstable because it doesn't have 18 electrons. Yep. So that just about wrap up our little exercise for counting of electrons for organometallic compounds, and I'm sure you can use the knowledge that you have gained to tackle the the 3 practice exercises I gave down here. So that's it. Thank you very much. I hope you have learned properly how to count electrons, how to assign the oxidation state of the metal just by looking at the charges around, and how to count the electrons, determine stable or not that compound. So that's it. Thank you very much. I'll see you in the next lecture. Assalamu alaikum.